Namaskar and welcome back to the course on statistical mechanics of phases and phase transitions. So we are in the last chapter and we have covered a variety of things in the course. So we motivated the course by talking about phases and phase transitions and pointing to the universal properties of many continuous phase transitions. We learnt about symmetry, scales and the central importance of interactions between degrees of freedom to get distinct phases. We learned how to characterize phases using symmetry and we introduced the idea of broken symmetry and order parameter. We learned about how to analyze models using variety of techniques. These included series expansions, in some very fortunate cases exact solutions. We learned about the notion of duality. We then went on to look at quantum systems and showed that statistical mechanics of d-dimensional quantum systems can be mapped to statistical mechanics of d+1 dimensional classical problems with probably different coupling constants. We learnt about the non-perturbative approximation methods. Particularly we learnt about mean field theory, which is actually very useful in many practical applications. We then went on to explore phenomenological approaches to describing the physics that we see, and we explored Landau-Ginzburg theories, and the main point there is that Landau-Ginzburg theory is successful in explaining the overall physics, but it does not get the critical exponents right. We learnt about the ideas of upper and lower critical dimensions, and we learnt about the Mermin-Wagner theorem, which says that in low enough dimensions and you have a continuous symmetry, it cannot be spontaneously broken at a finite temperature. All these ideas of universality and all the fancy phenomena that we know about critical exponents, all of those can be explained by the scaling hypothesis, which makes the statement that the free energy or the non-analytic part of the free energy is a generalized scaling function, and from there we were able to derive all the scaling laws, which are relationships satisfied by the critical exponents irrespective of which universality class they are. And this whole story culminated in the renormalization group idea, which uses just one central notion, which is that at a critical point you have the system develops a scale invariance as an additional arena symmetry, and from there everything else follows in a sense. And we explored Wilson's renormalization group, and Wilson showed how one can understand how the short wavelength fluctuations, how they affect the long wavelength properties, and not only does it give the conceptual framework for understanding critical phenomena, it also allows us to perform calculations and extract critical exponents, which we have done in the course. And we explored variety of other theories as well. For example, we learnt about the nonlinear sigma model, which is again a very important model that has helped us understand a variety of phenomena. And we also explored the Berezinski-Kosteles-Thouless phenomena, which is what happens in two spatial dimensions of the classical XY model, where there is a phase transition without any breaking of symmetry, and this kind of phase transition is actually driven by proliferation of topological defects, which is a fairly interesting and exotic phenomena in a sense. So this is where we are. So in a sense we have seen what is sort of thought of as traditional phase transitions and critical phenomena and all of that. So what I thought we could do in the final chapter is to look at some sort of contemporary applications of these ideas, and in this chapter we will start exploring one of the very interesting things that has come about in the last, say, let us say 20 years, where we have understood that quantum information processing is the next thing or the next revolution, and I will briefly introduce these ideas and what I am hoping to do is to whet your appetite to explore further. So this lecture will certainly be very if you like very summary like. I will not get into too many details, but I will try to explore the overall scenario for you. And this is with this goal, let us jump into the idea of what are quantum computers and all that. Of course, I have just one slide on this, so it simply does not do any justice to quantum computers, but I hope to give you the idea of at least in some very brief way. So modern computers like the one that I am using to give this lecture is based on storing information by bits which take values 0 or 1, and there is a whole set of logical operations we can do on these things, and we can perform computation. Those are well defined and very well explored notions in computer science. So you can perform computations and you can ask questions and find answers and so on by developing algorithms to do that. Quantum computers, they think of information in a more continuous sense, if you wish. So instead of this classical bit which takes values 0 and 1, a quantum bit is a two-state qubit, as we have seen in this course before. It is a two-state system which can be put in a vector linear superposition of these two states. So there is this idea of superposition, and when you have superposition, if I have, let us say this state is called 0 and 1. So if I produce a state alpha times 0 plus beta times 1, where alpha and beta are complex numbers such that the modulus of alpha square plus beta square is equal to 1, that is modulus of alpha square plus modulus of beta square equal to 1, then I can encode information into that by choosing the phases and amplitudes of alpha and beta, and this qubit will have some state which encodes that information. The problem with qubits is that since it is a two-state system, there are all kinds of perturbations that can show up on these, and that can actually change the levels of this 0 and 1, and it can produce phase changes of phases of alpha and beta. Those are problematic. It can change the amplitudes of alpha, beta and so on. So if you initiate a qubit in some initial state and just leave it there, over a period of time it will simply go to some other state because of environmental factors, all kinds of things that will talk to the qubit in a sense, and the qubit is supposed to, which we do not control in a way. So this leads to the problem of the qubit being decohered, and this decoherence of qubits is a very big problem, and it leads to loss of information. So if indeed we can handle this decoherence in some way, or we can mitigate the decoherence or find ways to work with the decoherence in whichever way you want to approach this, you will see that once all of these problems are tackled, you are going to go to a place where there are the quantum computers that will be able to solve very complex problems which can't be dealt with in classical computers, and it is believed to be something like an epoch changing event, and it could be like things like discovery of vaccines or discovery of electricity or something like this. It's going to have such importance in the evolution of our civilization. So that is the background, and as you can see, the central question here is how to keep the quantum information that you store in this quantum system safe from decoherence. So this is in a sense the question. So what I am going to present to you today is I am going to show you how you can construct logical qubits, that is, you can construct systems whose states will be used as the qubit states from a collection of such decohering qubits, such as these bad qubits that we have which are decohering for whatever reason. the idea is to put many of them together and let them interact so that you get a certain phase of those qubits, right, phase as we have studied in this course, and we can use the properties of that phase, and I will show you that the property of that phase is something very interesting. It has some certain kinds of degeneracies, and those degeneracies can be used as the states of the qubit. And so this is the idea of what I am going to discuss today. So we want to create a system of interacting qubits which will go into a phase which has certain degeneracy, and this degeneracy will not be arising from any kind of symmetry. Typically, for example, if you study hydrogen atom, you can see that certain angular momentum level will have certain degeneracy coming from some, from the fact that there is rotational symmetry. So the degeneracy there arises from symmetry, and typically in physics degeneracy does arise from symmetry. So what we will see here is that this degeneracy will not arise from some global symmetry, and we can use this degeneracy to build qubits, and this degeneracy, since it is not coming from a symmetry, some local perturbations cannot change this degeneracy, and therefore if I put information in those degenerate states, local perturbations, things that I have no control over, cannot change this degeneracy, such as what will happen in a simple 2-level system. In a 2-level system, suppose I have some stray magnetic field, something coming up from some, there is some disturbance of some kind, some electromagnetic disturbance, then it will split this the 2 levels, and this is why it decoheres. The question is, how do we do this? So I am going to introduce this from a very physics perspective, admittedly, and I am going to introduce something called as the Z2 gates theory. So this is a quantum model, and let's see first what this is. So the arena for this model is the square lattice in 2 spatial dimensions, and I use periodic boundary conditions. So the square lattice you can think of as being wrapped on a, so there is a torus which is the periodic boundary conditions, we have seen this before, and the square lattice sort of tessellates this torus. Now if I am going to think about the usual Ising model, I will put the qubits on these these sides of the square lattice. But what we are going to do here is we are going to depart from that, and we are going to place the qubits on the edges or links of the square lattice. Okay? And what is the Hamiltonian we are going to write down? So the Hamiltonian we are going to write down. So first of all, if I have a set of if I have a system with L1 sides along the one direction and L2 sides along the other direction, then a total number of sides in this problem will be L2 times L1, and the number of links will be 2 times L2 times L1, and at every link here I have put a qubit, and so the Hilbert space is simply the tensor product of all the Hilbert spaces of these link Hilbert spaces, and the dimension of that is 2 times 2 L1 L2. So 2 L1 L2 simply counts the number of links. So what is the Hamiltonian? So the Hamiltonian can be written down like this. This H has a product of 2 terms. So this J here is this something like we call exchange coupling in Ising language. So here it should be thought of something like a magnetic term, right. So it's a Gates theory, so we are sort of being inspired here by electromagnetism. So just believe me, I'm not getting into the details of this. So this is like it's like the B square term. So if I were to connect this to electromagnetism, the Hamiltonian of electromagnetism would be E square, or Hamiltonian density would be E square plus B square with suitable coefficients. So this is like the B square term here, and this is like the E square term here, very crudely. Okay, and so there are some coupling constant here. We call this J and H. This is pretty conventional in this field. So this is the Hamiltonian, and so what is this BP? The BP, P is what we call a plaquette. So this is the plaquette, and this BP here is the product of all the Zi operators, the poly Z operators on all these 4 qubits. So that is what we call as BP. And at this site I, there is the Xi operator, and that is the Xi Pauli operator, and that is the operator associated with that. So the terms are associated with plaquettes and these qubit along the links. Okay? So that is the Hamiltonian. So now what is the symmetry? Yeah, so I just mentioned this, that the BP is the magnetic field and Xi is the electric field, and J and H are some coupling constants. And what I would like to impress upon you is that this system has a very interesting symmetry structure if you just view this as some Hilbert space and ask what are the operators that leave the Hamiltonian invariant. So I invite you to explore this. Imagine that S is a site, this site S. You associate with a site S an operator which I call as AS. In this field it is called as the star operator. So this is called the plaquette operator and this is called the star operator. So if you think of this as the AS operator associated with the site, that operator is defined as the product of Xi, the Pauli Xi operators of all the qubits that are touching this site, if you wish. So that is this notation. So I touching P means the link that touches the plaquette. I touching S means the link that touches the site. So there are how many operators like this? There are as many operators as there are sites. Now what you will find is that the Hamiltonian, and you can see that these are unitary operators, and so if I do a unitary transformation of the Hamiltonian, a unitary transformation can represent a symmetry. So you will see that it will leave the Hamiltonian invariant. So it appears that there are a very large number of symmetries in the system, and there is in a sense the symmetries are local. The transformation, so for example AS, when it acts on this full Hilbert space, it will make changes only in the Hilbert spaces associated with the links that are connected to the site S. So these are in some sense local symmetry transformations, and this is why we call it a gauge theory, connecting to what is done in high energy physics, for example, or even electromagnetism. Okay. So there are all these symmetry operations, and what I will invite you to explore is, for these AS to be a symmetry, you do not need translational invariance of this Hamiltonian. So for example, you could make these J's as plaquette dependent, let us keep them all positive for now, and similarly H you can make it to be link dependent, and even then you will see that this is symmetry. Okay. So this kind of a theory with this local symmetry is what we call as a gauge theory. Okay. Alright. Now let us study some properties of the operators that we have discussed. So you will see that if you look at this plaquette operator, the plaquette operator is a product of 4 Z operators on the 4 link qubits. If you square that, you will get 1. It just comes from the properties of Pauli operators. Similarly, if you square the AS operator, you will get 1. If you square the X operator, you will get 1. So all of these are nice operators that we are in some sense familiar with. Now if you look at any BP, any plaquette operator, and take any other plaquette operator, because they contain only Z operators, they will commute with each other for any 2 plaquettes. Similarly, the X's will commute, AS's will commute, and now comes a very interesting thing. AS will commute with BP, and the reason for that is, if I take a plaquette, if I take this plaquette, and if this is the S, there are 2 X operators that are involved. So when you do the algebra, you will see that it will just commute out, because there are 2 X operators involved, and that is why AS commutes with BP. And AS and Xi will also commute. Of course that is not surprising, because AS is simply made of Xi's themselves. Now BP and Xi, if the link I does not touch P, will commute. So for example, if I have this link I and this P, then of course this has nothing to do with this BP, and therefore it will commute. But if instead of this I, if I had chosen this site as I, then that will anti-commute with BP. You can check this yourself. This will anti-commute with BP if I touches P. So this is the algebraic content of the theory, if you wish, in terms of the operators. Now in addition to all these very nice properties that we have, you will also see that there are certain, if I may say, topological constraints on these operators. So if you look at the product over all plaquettes of BP, because I have periodic condition, boundary conditions, you will see that and BP's commute with each other, every Z operator that you have associated with the link will appear twice and it will square to 1, and this product itself will become 1. Okay. So this in some sense is some kind of topological constraint on these BP's, as you will see, and this of course repeated, this is redundant, you can ignore this. So product AS is also equal to 1 for the very similar reasons. So then now the question that we would like to ask is, what is the ground state as a function of H by J? So this is the question we will ask, and we will not answer this question in great detail. So for example, I am not going to look at what happens when H by J is very large and so on. That is a very interesting problem in itself, we will not go there, but let us at least look for what is the ground state and what happens, what is the physics when H is much less than J. Okay. So we will start with something simple. Let us start with H is equal to 0, and you will see there is only BP in the Hamiltonian now, and so we will want, and every BP commutes with every other BP. So the ground state, because J we have chosen to be positive, the ground state will be such that every BP has an eigenvalue 1 on the whatever state that you have as ground state. So what is a possible state you can choose for that? Well, you go to every qubit and put them all in the Z up polarized state, and you can actually pick that as the ground state. Just very simple and straightforward. Okay. So if you now look at what are the excited states of the system, you will see the excited states of the system have plaquettes where BP will be -1. Okay. And such plaquettes where BP is -1, indicated by this light green color here, are called as monopoles. Yeah, they are motivated by the word magnetic monopoles. So they are called monopoles, and because remember the product of all BP's have to be 1, and that means that in this if you put this theory on a torus with periodic boundary conditions, you will see that these magnetic excitations can only appear in pairs. Right. And so for example, how do I create this magnetic excitation? So I take this ground state and I hit an Xi. So you see this, so I have hit this Xi on this, that is why this I is blue in color, trying to match the color of this link here. So when I hit this Xi, it will flip the spin from whatever it was in the up state, it will go to the down state, and now you will see the BP will become negative here, BP will become negative here. And this will cost an energy of 4J, 2J for this plaquette and 2J for that plaquette, and you will cause an energy of 4J. So this excitation is gapped. Okay. So this is the physics when we are H much small, when we are literally H is equal to 0, this is the situation. So based on this, how can we say something about the quantum physics of the system when we are at a finite H? Okay. So I am going to explore this very briefly. You have to, I hope that this will motivate you to look up the literature and explore more of this. So for H much less than J, we can actually find an effective Hamiltonian motivated by the excitations etc. by the following way. My claim is our H is equal to 0 state, the ground state has BP equal to 1 everywhere. I am going to claim that if I apply 4 x operators, remember when h is not equal to 0, the perturbation is minus sum over all the links h times xi. So I want to see what is the effect of that term on this ground state that I have. So I am going to claim that a action of 4 xi operators centered about the site, this is the site, will bring me back to the state I started off with. So let us see. So I apply xi on this line here first. So what happens, I create these 2 monopoles. Then I apply xi here. So this monopole is now killed because you see now this placket has 2 down spins. So that will produce the same BP, up, up, down, down. So 1, 1, minus 1, minus 1 will produce 1, that is why this is white. So this placket has been pushed up now. This monopole has been pushed up. And now what I do is I apply the x operator on this, right, and then finally apply the x operator on this back again, and now I see I have killed the monopole back and I go back to the vacuum, in the sense no monopoles. So what I have now done is I have gone from I found some term in the Hamiltonian which connects which brings the ground state back to the one that I start off with, etc. And based on this you can actually work out that the effective Hamiltonian up to some order in perturbation theory in H, in fact the 4th order in perturbation theory, can be written down like this, right. So this is J times BP, this is exactly our old term, minus K times sum over S AS. Why AS? Because these 4 xi operators actually produce the operator AS. So that is what this is, and this K goes as h to the 4 by j cube. So h is the perturbative piece of the Hamiltonian and j is the energy denominator, and this is how you get this K. So if you work a little bit you can find the exact expression for K, exact expression meaning you can find the numerical factor that sits in front here. Okay. So this model was introduced by Kitaev and it is called the Toric code. Toric code because it sits on a torus. Code because that is where we are going to store information. Okay. So this is called the Toric code. So let us explore what is the ground state of the Toric code. So what we are going to do is, remember that if we want to solve some problem, say hydrogen atom, the way we do this is we find out the symmetries and then we find the symmetries, from there we find what are the the good quantum numbers, namely say for example angular momentum is a good quantum number. So we can label the states by the quantum numbers of angular momentum, and we are going to follow exactly a similar strategy here. So we notice that AS commutes with the Toric code Hamiltonian and AS is a Hermitian operator. So the eigenvalues of AS, remember there S runs over all sides. So there are L1 times L2 number of AS operators, each of them can take plus minus 1 eigenvalues. So we can label states using the eigenvalues of AS. Similarly we can use BP to label the eigenvalues of the eigenstates of the Hamiltonian, and the eigenvalues of BP can be used to label the eigenstates of the Hamiltonian. And since AS and BP commute, we can find simultaneous eigenstates of AS and BP and they can be the states of the Hamiltonian, right. So this is the state. So now let us find out how many distinct eigenvalues are possible for the set of all BP. Remember there are L1 times L2 plaquettes, but the point is, and BP squares to 1, so BP can take eigenvalues plus and minus 1. So you may naively think that there are 2 to the power L1 L2 different possible values of the eigenvalues of BP, but that is not true because there is a global constraint, you have to remember that. It comes from the fact that product of BP equal to 1. So that means only L1 L2 minus 1, that is only the number of sites, if you wish, L1 L2 minus 1, only those minus 1 are independent. This means if I list out all the eigenvalues, all the correct eigenvalues of BP, there will be 2 to the power L1 L2 minus 1 sets of them. So similarly, if you look at AS, you will have a very similar set of L1 minus L1 L2 minus 1 number of these. Now if you can, we can easily count the degeneracy of a system in the following way. So we know how many distinct sets of quantum numbers we can have. So the number of distinct set of quantum numbers is 2 L1 L2 minus 1 times 2 L1 L2 minus 1. This comes from the BP and set, and this comes from the AS set. And if you look at the dimension of the Hilbert space, that is 2 power 2 L1 L2, that is just 2 power number of qubits, that is equal to number of links, which is 2 times 2 L1 L2, and you will see that this is 4. So we now find this beautiful result that every state of the system is degenerate by 4. In particular, the ground state is degenerate by 4, right? And the remarkable thing is that this degeneracy does not depend on any symmetry. So you might think that, okay, I have solved this problem because I have some I have some translational symmetry or something like this, and it's giving some degeneracy of 4. But I would urge you to look at the following problem. Remember, I had asked you to check whether the gauge symmetry was a symmetry of the system when you didn't have translational symmetry, and yeah, I made the J's plaquette dependent and the H is also link dependent. You just keep all of them positive for now, but make them kind of random, and you will see that this 4-fold degeneracy will still hold. So this really does not depend on any symmetry. And in fact, it does not depend even on the square lattice. In fact, I would urge you to, this is a very interesting problem. You can take some arbitrary tessellation of the torus, like the one that I have shown here, and you can define a theory where there is a plaquette term associated with the product. If this is a plaquette now, some kind of random plaquette, then you take the side, the links that are bordering this plaquette, and simply take the product of all the Z operators and minus h times xi associated with each link. You will get a theory which is the Z2 gauge theory, and you can show that this has exactly the degeneracy of 4 if this random set of thing tessellates a torus, that is, it covers a torus without holes and stuff. Okay. So this is an extremely robust degeneracy. It does not come from any symmetry. So what that means is, I can locally perturb the system. That is, if I have, even if I go and show some, if the h is time varying or something. If, for example, the h at some point at some site has some fluctuation, it will not affect this because this degeneracy is robust. So such a degeneracy is called as topological ground state degeneracy, and it's called so because the degeneracy only depends on the underlying manifold, right. So we chose the torus as the manifold, and the torus is a genus 1 object. Genus means it has one hole. So you can actually work out some very nice things. So suppose you take this Toric code and put it on a genus G manifold. So for example, that is like some kind of double torus or some triple torus or something like this. If you do that, you can show that the ground state degeneracy goes as 4 to the power G. So indeed, this is truly, the degeneracy is in some sense dependent only on the topology of the underlying manifold. So this is called as the topological ground state degeneracy. Okay, so what is the conceptual idea here? The conceptual idea here is, since this ground state degeneracy is not broken by local perturbations, what we can do is we can choose these degenerate ground states as the states of the qubit, right. So you may think, oh, there are 4 of them, how can I get a qubit out of it, right. So the idea now is, I have not shown this explicitly in this, and I invite you to explore this. So in the discussion that we had so far, we put periodic boundary conditions in both directions. So there is periodic boundary conditions in the one direction as well as in the 2 direction. Suppose you were to break the periodic boundary condition in the one direction, then you will just, if when I put periodic boundary conditions, I will get like something like a cylinder with chopped off ends. So it will be like an open cylinder. So that is called as, many people call this the surface code, and you can show that that has a degeneracy of 2. So if you use the twofold degeneracy of the ground state, and that is so robust, it can't be disturbed by local perturbations, you can use the phase meaning the state that is obtained by all the interactions between the qubits as shown. You can use those two states as the logical qubit where you are going to store information. So you can put all these bad qubits together and produce a very robust topologically protected qubit. So this is the idea of a topological quantum memory very briefly, right? And since I am also from the physics background, I would also like to advertise some very interesting physics that comes out in this Toric code. So the first thing is that we can write down a ground state for this Toric code in the limit that we have discussed. I have not shown that here, but you can show that that has some very interesting entanglement property, and it has an extra term other than what is conventionally called as the area law entanglement, and there is a term, there is a constant negative term called as the topological entanglement entropy, which is actually a characteristic of this state. Okay, it is something universal, you could say. Okay. So you can also study the quantum properties of these excitations. So we had these monopoles and charges. So you can show that these monopoles and charges are bosons. What do I mean by bosons? So if I have two of them, if I exchange them, I will get a phase of 1, right. On the other hand, if I take a monopole around a charge, then it will pick up a phase of -1. In other words, if I exchange them, I will get a phase of I, that is square root of -1. So these are called mutually semionic particles. Mutually semionic particles. They are not identical particles. They are, both are bosons, but different kind of bosons. The charges are of course the one where the monopoles are where the plaquette is changed to -1. Charges are where the star operator picks up a -1. So they live on the sides, the charges. And if you take a monopole around a charge, then the overall phase, you will come back to the same quantum state but with a phase of -1, and this is why they are called mutually semionic. And now there is something far more remarkable here. So if you now make a bound state of this monopole and this charge, so these are called Dyons, and if I take one Dyon around, if I exchange two Dyons, I will pick up a minus sign, and that means that Dyons are fermions. So you can imagine something remarkably beautiful, which is that you start with a system of qubits, and you have in the excitation spectrum of that qubit system, there are fermions. So in some sense fermions emerge as excitations of this qubit system. Okay, so you can see that this is actually a pretty rich problem and very rich system, and this is an example of what is called as a topologically ordered phase of quantum matter, and it is a very active area of research. So I must also emphasize that many of these ideas have been realized in the laboratory by by groups like the Google Quantum Initiative and variety of other groups who are exploring how to bring quantum computers to life in a sense, and a lot of exploration has taken place. So I hope that this discussion will whet your appetite to explore further. Okay, so everything that I have discussed so far is at 0 temperature. So we have been talking about ground state. So what I would like to show you is I would like to connect up some of the ideas that we have discussed in the course before and show you how we can use those ideas to analyze what happens to this system at finite temperatures. I have to emphasize that the discussion that I am going to have is going to be very overview type, and I am not going to show you any kind of mathematical details, and I invite you to explore some of these ideas first by yourself, and if you find the going difficult, then you could refer to things in the literature. So physics at finite temperature. So if I want to hold on to the full quantum problem, then I will not be able to discuss it at any level, at least in the short span of time that we have for this lecture. So what we will do is we will go to h is equal to 0, where the problem is really classical in a sense, because the operators that are involved, they all commute with each other. So we can think of this problem classically. So if I look at the BP term, it is a product of all z's. So if I simply work in the basis, eigenbasis of z, so we can think of the degrees of freedom as Ising spins. So on the same lattice that I had, you can imagine a problem, this problem where I had Ising spins. So instead of qubits here, just put Ising spins here, and you define BP as simply the same product of all the Ising spins on the plaquette touching and product of SI. So given some configuration C of these links variables SI, I have a Hamiltonian which is just exchange coupling times BP. So now this problem has exactly the same gauge structure or the gauge symmetry that we had. So you can go to a site and apply AS. What AS will do is it will go to a site, it will find all the links that touch the site, and it will simply change the spin configuration of all those 4 links that are touching the site to the negative of them, and you will get a new spin configuration C tilde. And you can see that this will have the same energy as this, because BP does not change upon action of AS, right. So this is the idea, and so this is why we call it gauge symmetry. Okay. Now the first very important result is that we call it Elitzur theorem. So such a local symmetry, remember why do I call it local, because there is a symmetry operation associated with every site, and each of them can be thought of as an individual symmetry generator, and the whole symmetry group is generated by products of all of these things. And the statement is that you cannot break a local symmetry. So this goes by the name of Elitzur theorem. Now it sounds very fancy, but it can be visualized in a very simple way. So the way you can think about it is, you can just go to a site and you can go to this problem and just apply some magnetic field at a site, and you can try to ask what is the expectation value of the magnetization, and you can show by a set of calculations that when the magnetic field goes to 0, whatever be the system size, that magnetization associated with that site will go to 0 when the magnetic field goes to 0. This is like our idea of putting a symmetry breaking field and asking whether the magnetization remains even when we turn off the symmetry breaking field. So you will find that it will not remain and it will go. Okay, so this is the statement of Elitzur theorem, and I am not proving it here. I do not want to rob your joy of discovering Elitzur theorem yourself. So please try this, it is a very interesting exercise. Right. So what this tells us is that the bigger picture that Elitzur theorem tells you is that if you construct objects, if you construct observables that are product of these SIs, such that when you do this, when you do any AS transformation on it, if it changes sign, that means that it transforms non-trivially under AS, then that object will pick up an expectation value of 0, and therefore it is not a really useful thing to look at. So what you should look at are those objects which, when AS is applied, will remain invariant. These are the operators that we should look at, or these are the objects or operators, operators in a general sense of, even if you were to do quantum mechanics. Those are the ones that you should look at. So what are those kind of operators? So these are these objects that do not change under the action of AS are called gauge invariant quantities. A very good example of a gauge invariant quantity is this BP. So if BP does not change, because if I apply AS, then at most 2 spins will change, right? Two spins or the 2 Ising variables on the links that touch the site S, they will change. So BP itself will not change. So BP itself is an example of a gauge invariant object. As you know from electrodynamics, magnetic field and electric field are gauge invariant, and it's in the same spirit that B is like a magnetic field and is gauge invariant. So the kind of quantities that are gauge invariant, I will just introduce them. They are called Wilson loops. So the simplest Wilson loop is a plaquette. So BP, that's the product of 4 spins on a plaquette. A more general version of this is the following. You define a line L on the lattice like this, and you take the product of all the S's that live on this line here. So if L is that line, you take the product of all S's that live on that line, and just a moment's thought will tell you that that is also equal to the product of all the BP, all the plaquette terms that are inside. So this is something like Stokes' theorem, but that is what it is. So this is the analog of integral of A dot dl is equal to integral B dot ds, that kind of stuff. That is what we are talking about here. Okay? And you can show very easily that this WL is actually gauge invariant. Okay? So now what is it that I am trying to emphasize here? I am trying to emphasize that the phases of this theory cannot be described by conventional order parameter, right. The conventional order parameter would have been something like a broken symmetry state or something like this, right. So I am finding that you cannot break any symmetry at all here, right. So we cannot discuss the phases of this theory in terms of order parameter, etc. So what you will find is that the behavior of these objects like WL, that is what will determine what is the phase in which this theory lives. Okay. So the phases of this model will be characterized by expectation value of WL, and so here these are examples where we are going beyond order parameters as ones that classify phases. We have already done that in the Kosterlitz-Sauer's case, but here is another example where phases will not be distinguished by order parameter but by some kind of correlation function. Okay. So if you find that the expectation value of WL goes as exponential negative of some number, this hash means some number, times A of L. What is A of L? A of L is the area enclosed by this. Then we say that this theory is in the area law phase. So when this expectation value of this Wilson line, when it looks like an area, then it is like saying that we are in the area law phase. There is another phase which is called as the perimeter law phase, which will not show up in the model because we are in 2 dimensions, but if you wrote the same model in 3-dimensional cubic lattice, it will have a perimeter phase also. So I am not discussing that explicitly here, but there is another phase possible in such theories in higher dimensions but not in 2 dimensions, which will have another phase called as the perimeter law or non-area law generically. Okay. So without getting into the details, I'll just advertise a fact. The fact is that if I have area law, then that will not allow me to have all the interesting topological stuff, etc. that I had. Okay. So the question is, what happens to my quantum memory which I had constructed at 0 temperature? If I go to finite temperature, of course I do not have H here, but one can argue that whatever arguments I am giving will also be true at finite H. So, we can still proceed with this. So the question is, does my quantum memory have a non-area law phase when I go to finite temperatures? This is the question. And the reason why I am interested in this is that the area law phase will not support all the interesting stuff that we had seen before, at least not in the thermodynamic limit, if I want to be very precise about this. Okay. So how do we analyze this problem at finite temperatures? So let us start at 0 temperature. There we know that WL expectation value is 1. Why is that? Because WL is simply also the product of all the plaquettes BPs, but BPs are 1 in the ground state. So it is exactly 1 with even the expectation value is there, it does not even have any uncertainty. I mean it is exactly 1 even in the Toric code, even when we included for certain quantum effects. So remember, this is not independent, this is actually independent of L itself, it does not even matter which loop you are taking. So it certainly does not depend on area, and so this is not an area law. So at 0 temperature we are not in area law phase, and all the spectacular topological stuff that we talked about, it survives. So how do I study this problem at finite temperature? So I am going to run through this very quickly. I could have done a more detailed thing, but then that will again rob you of the opportunity to explore this yourself. So let me just outline the idea for you, please try to do this calculation yourself. So to study the finite temperature properties, the trick that you have to do is to do something called gauge fixing. So this is something that you are very familiar with when you studied electrodynamics. So if you want to study typically any electrodynamics problem, so what you would do is you would choose a gauge, you could choose a Lorentz gauge, Coulomb gauge, whichever gauge you which is convenient to do calculations in, you choose that, and then you study the problem because you know that the answer does not depend on the gauge you choose. So we can do exactly the same kind of idea here, and what we do here is, you see, we can think of the Ising variables to be on horizontal links and on vertical links. Now whenever an Ising variable is on a horizontal link, I just set that its value is +1. That is like choosing a gauge. Okay, if that is not obvious to you, you can just think about this and you will realize that that is indeed the case. That is like choosing a gauge for the problem, and we can just set these things to be +1, right. So the blue sides have been set to be +1. Now what is the Hamiltonian? The Hamiltonian now is the product of spin, spin here, spin here, spin here, that is the plaquette term, but these are 1. Therefore what I will get is, I will get just the product of this red spin and this red spin. Similarly plus this red spin plus this red spin. And now you will see that this spin here will not talk to the spin there because I have gauge fixed. So what do I have now? I will have a set of uncoupled Ising, one dimensional Ising chains. So when you gauge fix this problem becomes a set of one dimensional Ising, uncoupled Ising chains. And because it has become one dimensional uncoupled Ising chains, I know exactly how to solve this problem, so I just solve it. And I can then use that solution to compute the expectation value of this Wilson line operator, and I find this spectacularly beautiful result that it satisfies area law with this coefficient here. So now you can convince yourself that if beta goes to infinity, which we go to, this is at 0, then this thing will go to 0 because cot h will go to 1, and I will get back this result, that you can convince yourself. But if you are at any finite temperature, you will see that it will satisfy area law. At 0 temperature it does not satisfy area law, but at any finite temperature it satisfies area law, right. So please work out this result, it is very straightforward. It may look a little intimidating to if you just stare at it, but if you stare at a little bit more, it will yield to your efforts and you will be able to get to this result. Okay. So what this means is that if I take, of course this, remember all these results are in the thermodynamic limit. So if you have a very large system, you will see that the topological properties will not be stable to finite temperatures. So how do we understand why this is happening? So remember I said that you can have these monopole excitations with energy 4J. So suppose I had 4J excitation, but you see these monopoles by single spin flips they can actually move around. To go from this configuration to this configuration, I just do a set of spin flips which do not require any energy. So what can happen is that these monopole excitations can start exploring the full all the different plaquettes, and they can gain entropy in very similar way as the domain walls of the one dimensional Ising model could gain entropy, right. So one dimensional Ising model, if I created a domain wall something, then I could move the ends of the domain wall with costing no energy. In a very similar way, you can see that once you create these monopoles, you can move them around, and that will cost you no energy but gain a lot of entropy. And this is the reason why this Toric code topological order instantaneously melts. And you can see that all the results, in fact this kind of expression itself was encountered in the one dimensional Ising case, right. So this is, you now see that all the information or all the ideas that we developed in studying 1D Ising model, etc., is in fact useful in understanding the finite temperature properties of this quantum memory, at least at some qualitative level, right. There is more to this when we go to quantum, and one has to explore this further, and one has to then keep in mind that these things are around when you are trying to design and try to produce an actual memory, etc. Okay, so this is how far I would like to take you on this problem. So let me quickly summarize what we have done. So we have taken a very brief glimpse of quantum memories, and it was motivated by the problem of qubit decoherence, and the essential idea that was used is to create a new phase of many interacting qubits and produce a state which has degeneracies which are not protected by any symmetry and therefore stable to perturbations. So this leads us to the famous Toric code, and not only does it is useful from the perspective of memory in terms of applications, it has many other very interesting physics things that I talked about, like topological order and so on. So today we understand this as a distinct phase of matter as compared to something like an insulating phase, but a different kind of insulator than what you will have otherwise. Insulating, by the insulating I mean gapped phase, right. Okay. So what we did was we used the ideas developed in the course, and we were able to explore at least get an outline of how to explore the finite temperature properties of such a model, and we came up with this idea of no spontaneous symmetry breaking. Very similar to that, there is no area, there is no topological order, or there is no the area law emerges instantly at any finite temperature, destroying this state. So this is also an illustration of how to study systems where phases are not distinguished by symmetry. So this is also a very nice example. So here the phases will be distinguished by certain correlation functions. So an example of this is this Wilson line operator. So this 2-dimensional problem is not rich enough, but if you put this problem in, if you take the problem to 3 dimensions, if you put the same theory on a cubic lattice, you can see that low temperature the Wilson line operator will have a different dependence on L as compared to at a higher temperature, where it will become area law like. So there is actually a true phase transition without any symmetry breaking, etc. So these are some very important and interesting ideas, and I hope that this very brief exposure to this will excite you to explore more of this, and thank you for listening to this lecture. Have a nice day.